I mentioned yesterday that yesterday and today would be just teeny tiny extra sprinkles on top of our notations. Because of that, I expect that we'll end early today. So hooray for us moving through. Because here's what I want us to do. I want us to do one orbital notation, one electron configuration notation, and one noble gas notation. Just one of each, right? But while we do those ones of each, I want this new vocab, very easy vocab, to be on the tip of your brain. So for those of y'all at home, pause the video. This is what they copied at the beginning of class. So let's talk about it real quick before we do our three examples. First off, valence electrons. It turns out that all of the electrons of an atom can be categorized into two main types. You have the valence electrons, which are the highest energy. Hey, what represents energies? Letters, numbers, or arrows? Numbers, right? On your opening slide of us doing this stuff, you wrote down that the energies can be a number 1 through 7. So you already know how to find the energies of any electron in one of your notations. What this says is that when you look at a notation, all of the electrons in the highest energy level in that notation are called valence. Therefore, if we had an atom that had 10 electrons, that means some of those 10 would be valence. What would the others be? If they're not valence electrons, what are they? Inner shell electrons, which is news to you because you just wrote that down. So let's say, for example, that we had an atom with 10 electrons, and we figured out, in a way I'm about to show you, that 3 of them were valence. How many inner shell would you have? 10 total, 3 valence, 7, right? Because the rest are inner shell. Another interesting thing that's mentioned on your opening slide is that you can't have more than 8 valence. That's the maximum number. Why? I'm going to show you next unit why. So let's not ask that question yet. But yeah, 8's the maximum number of valence, but there is no maximum number of inner shell. So if I had an atom with 100 total electrons, only 8 of them, somewhere between 1 and 8 of them could be valence, and all of the others would be inner shell. Once you calculate how many valence there are, and it's very easy to do, then there's a secondary skill you can do, which is called a Lewis dot structure, which is a pictorial way of easily showing other scientists how many valence electrons, high energy electrons, a certain element has. So with all of that stuff in front of you, I'm going to switch the screen to our examples, and let's do our 3 notations, yeah? So here we go with our first one. All right, we're working together, but I want to do the orbital notation for iron, is what it says on the screen for those of y'all at home. The orbital notation of iron. Now, make sure you know what that means in regards to the types of notations. The orbital notation is the one where we draw arrows. It's the one with the arrows. It's the annoying long one. But my question isn't what's the orbital notation for iron. I mean, I'm going to make us do that. But my real question is, what's the Lewis dot structure of iron, which is something brand new. So let's get that. Somebody from cluster 1, how many electrons does iron have? 26, all right? So we know that we have to draw 26 arrows. Hey, somebody from cluster 2, where do we always start when doing any notation? 1s, except for noble gas, right? We always start at 1s, but remember we said that this is the notation with the lines and the arrows. So now we go back to your notes, flip back if you don't have it memorized yet, but I know that S can hold 1 orbital, and I know that Pauli said any orbital can hold 2 oppositely spinning electrons. So we've got our fun little sheet available. And I know that if we read it like a book, after one S comes 2S. And all of the S's always look like that when they're filled. Hey, someone in cluster 3, what comes after 2S? 2P. And I know that a P from my notes has 3 orbitals. And any orbital anywhere can hold 2 oppositely spinning electrons. Hey, cluster 4, can any of y'all tell me the scientist that said that we're going to fill these up, up, up instead of up, down, up, down? What's his name? I'm only talking to cluster 4. 4. No, not Alpha. What? Still not, okay. We're down to the last one. What's the right answer? Hund says that you go singly before doubly. So let's continue going. After 2P comes 3S, and we know what S's look like. From there, 3S skips across the gap over to 3P. And we fill him properly. We haven't gotten to 26 arrows yet or iron's location, so let's keep going to 4S. And finally to 3D. Hey, cluster 5 and 6, anybody, how many orbitals fit in a D? 5, because your notes say so. All right. But we could have looked and realized that iron is in the 3D block, so we know we're going to stop there. If you were to number the 3D squares 1 through 10, iron is the 6th. Yeah, he's the 6th square. So up, 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 up is 5. There's number 6. You can count the arrows if you want to. And now you're at 26. Now, we haven't done anything new yet. That's just review. Hopefully this is getting boring to you. I want you to be that good at it. But let's look at the real question. What is the Lewis dot structure for iron? Well, the Lewis dot structure, again, is a representation of valence electrons, the highest energy electrons. So, look here. We already said that the energies are represented by the numbers, the big numbers. Here they are. Here they are. You don't have to do this on yours, but here's all the different energy levels. I want to know, of all of those energy levels, which is the highest? I'm just looking for a number. Energy level. Don't be giving me letters. Those are cloud shapes. I don't care about cloud shapes. 4. 4 is the biggest circled number. Therefore, this 4 right here, all of the electrons with an energy of 4 are valence. How many valence electrons do you see? There's 2. Iron has 2 valence electrons. Those 2 arrows right there. What are all the other electrons called? Inner shell. All right, because all of the other ones, if we were to draw those circles like we would draw around the nucleus, all of the other ones are in orbitals that are closer to the nucleus. These 2, those 2, are in the orbitals that are furthest out, furthest away, because that's where the most energy is, which we talked about already once upon a time. So the other ones are on the inner shells, is the way to look at it. So iron has 2 valence electrons. Now, sometimes that's the question. And my questions might say, how many valence electrons does so-and-so have? You'd be done. It's not what I asked. I want to know, what's the Lewis structure? So here's what I need you to know about Lewis structures. If I had, don't draw this, just watch. If I had element X, all right, that was the symbol, and I wanted to max out the valence electrons available. What's the max number? 8. And here's where they could go. Right around the symbol, nice and organized, 2 max per side. All right, so this is what an element with the maximum number of valence electrons would look like in regard to his Lewis dot structure. But I don't care about X, I care about Fe. Hardest question of the day, are you ready? How many dots are we going to draw around him? 2. The number of valence electrons is the number of dots. But just like we do with Hund's rule, we're going to go single before double. It's better chemistry. But there it is, the Lewis dot structure of iron. Want to draw some cards on a new example? Yeah. Where's Aspen at? All right, here we go. New example, new example. We're going to do this together. New notation. We're going to do the electron configuration notation of tellurium, is what the screen says. Let's get some help already. Let's go over to cluster 6 and talk to seat 3. Hey, 6-3, what is the symbol and electron count of tellurium? Oh, dang it. Got ahead of myself. Yeah, how many electrons does tellurium have total? 52. All right. So if we were doing orbital notation, we'd have to draw 52 arrows, but we're not. We're doing electron configuration notation, which of course is the one with the exponents, right? Make sure you know that vocab. So let's get some help. Let's have someone spit out the first 3 steps. Let's go over to cluster 6 again. Seat 5. 1, 2, 3, 4, 5. Hey, 5. Where do we? Can you just start me off? 1, and now remember exponents, so it's 1s. 1s2, what comes next? After 1s2 comes, hey, I'm only talking to one person, y'all. 2s2, followed by 2p6, because remember, y'all, the cheat you can do there is just count squares, right? There's 6 squares in the 2p block, or a p has 3 orbitals, each one holding 2 electrons. Let's have somebody else pick up from there. Let's go to cluster 5 and talk to seat 2. Hey, 5-2, can you help me out? What comes after 2p6? Followed by, count the squares. How many squares are in 3p? 6, followed by, you can stop right there. Everybody all right? We're getting good. I'll keep going. After 4s, looking up there, we go to d. Hey, have y'all noticed this? Have y'all noticed how there's a drop in energy whenever you hit d? Look for those patterns. It happens every time. When you go from s to d, the energy drops a level. So make sure you recognize that. And then what happens after it drops down a level? It goes right back up to what it was in s, which is going to be 4p. 6 squares, 3 orbitals, 2 electrons each. After 4p comes 5s2, and then boom, we hit tellurium's block. Oh, no, we don't. 4d10, there's 10 squares there, 5 orbitals times 2. Got ahead of myself. Tellurium's block is 5p. If you were to label the 6 squares in 5p, 1 through 6, which numbered square is tellurium? Is the fourth one. Now remember, you can check your work, add up the exponents, they'll equal 52. But here's what my question is. Don't answer out loud because I want to draw the card. How many valence electrons does tellurium have? Privately come up with a number. How many valence? All right, let's head over to cluster 1. Hey, cluster 1. Aspen, stand by. Cluster 1, seat 3. Aspen, how many valence electrons is your guess? The guess is 2. Do you like that answer? No. Oh, I heard a yes. I heard a no. They're arguing over your answer. I'm starting to hear more no's. Somebody throw out a second answer then. They have all kinds of wrong answers. They're all so bad. No, there's the right answer is being said, but y'all are coming up with creative numbers. You can pass Aspen. There are 6 valence electrons. So why are there 6? Look here. I'm not going to circle them all again, but it's the big numbers that you're looking at. The biggest big number is 5. All right, we good? But that's not the only 5 because checky, there's another one, which means you must account for every electron with the highest energy, which is going to be those 2 and those 4 for a grand total of 6 valence electrons. Here's a fun question. Are you ready? Here's my next question. Drawing a card. How many inner shell electrons does tellurium have? Let's go to cluster 5 and talk to seat 4. Aspen, it's you. How many inner shell electrons does he have? 46 is correct. You can pass the burn. How did he get 46? Yeah, there's 52 total. 6 of them are valence. All the rest are inner shell, right? So 52 minus 6 is 46 is the best way to do it. How many dots are in the Lewis structure? Yeah, 6, right? So watch how I do it in case you're confused. You put the symbol of the element and then the number of dots. 1, 2, 3, 4, 5, 6. There's tellurium's showing up kind of light on my screen. There's tellurium's Lewis dot structure. All right, let's do one more and we'll have somebody come up to the whiteboard this time. Who's it gonna be? But now there's a video recording, so one of y'all can be famous, eternally famous. I'll turn it away if you don't want to be on YouTube though. So here you go, your final example. The screen says use the noble gas notation for cesium. The noble gas notation for cesium. Find the Lewis dot structure, y'all. Plus. There are never valence electrons hiding in the brackets. Do you understand what I just said? If you're doing noble gas notation like you are now, you don't have to be like, oh, well, I abbreviated. What if I'm missing valence? It's impossible. All right. So noble gas notation is still your best friend, and all of the valence electrons will be very obvious to your eyes after the notation. All right, so if I draw your card, you're going to come up to the whiteboard. You're not going to draw too small, and I want you to do the notation, and then I want you to put dots around my symbol there. Yeah? Let's see who's going to be famous. It's going to be somebody, man, Cluster 6, y'all are rocking and rolling today. Cluster 6, seat 1. Come on up, man. Come on up. You can bring your stuff if you want to. Would you like me to turn the camera, or are you okay? All right. When I monetize this, you get to, I get to give you a paycheck. 50%. Yeah, 50%. That's for drawing the dot. So draw the notation and then fix my symbol. Now wait for the camera. Do y'all agree with his work? Yes. It's perfect. All right, I'm going to darken it just a little bit because my screen doesn't pick up really well unless it's super dark. But all I'm doing is writing over his work, but what he did was perfect there. There's your noble gas notation of cesium, and, well, there it is, 1 valence electron.